Swayam Prabha. Digital India. Educated India.
Congratulations again. Best wishes to Professor Satyamurthy. This is work which was motivated by, whenever you do science, universality and semi-universality are some things are very, very useful, and if you can get them, it's fun. So, what we were looking for, obviously, I work in density functional theory, and there's been a lot of talk and trying to apply orbital free density functional theory to large systems, and Thomas-Fermi makes the first rung of that ladder, right? So we were asking, Thomas-Fermi has some beautiful features, and it's fun to go through them. So we were asking if there are solutions other than atomic systems where it gives you universal kind of behavior. And so let me just, what I'm going to do is motivate the whole thing in the first part, give you a little introduction to Thomas-Fermi theory, and then go over to recent work. The Thomas-Fermi theory is the simplest of approximation which approximates electronic kinetic energy in terms of the density. This is given by Thomas and Fermi way back in 1929 and 1930. And the only part that it takes care of as far as the electron-electron interaction is concerned is the Hartree part. So it's the simplest one. No exchange, no correlation, pure kinetic and Hartree. Okay, the total energy is written as this functional in terms of the density. This is the kinetic part, the Hartree part, and whichever external potential one is moving in. The equation comes from variational principle. So this is the equation. This is the kinetic pressure, if you like, kF square by 2, the Hartree potential, and the external potential. It should all add up to the same thing, which is basically saying that the uppermost energy has to be the same throughout. Otherwise, system can minimize energy by moving from one side to the other wherever the energy is larger. Solution, if you solve it, gives approximate ground state density, approximate ground state energy, and the ionization potential, which is negative of the chemical potential. And as I said, people still play around with it, and that is, I'm giving you some references. The Larry Spruck in 1993 Reviews of Modern Physics. This is particularly for students. It's a fantastic article which gives you the whole range where Thomas-Fermi theory can be applied, starting from atoms to neutron stars and things like those. Norman March wrote this paper, which is also a very nice introduction. Lieb's paper in, cannot be this is 1981. Again, Reviews of Modern Physics, where he proves many, many important theorems for this. This is a very important paper making use of universality of Thomas-Fermi theory. And I'll show you that graph where they produced a universal photoabsorption curve for atomic systems. And this is a computational, very important paper. So first thing that, past 2 days you've been hearing about many advanced things. So first question I want to answer is it really even worth talking about Thomas-Fermi theory in 21st century? And the answer is no. I'm here, and I'm reasonably intelligent, so I'm doing it. That means it must be okay. There's a lot of computational power available, but we still want to do it because no matter what you do, there are always going to be systems that are difficult to handle. So you do need to look at these approximations, which become exact in certain limits, and they teach you a lot. They help you develop some sort of mental picture. So why study? As I said, regardless of computational power, there will always be bigger problems to solve that necessitate applying orbital free density functional theory. There's a zeroth order approximation for this theory. It can be applied with equal ease all across the system. I talked about that reference article by Larry Spruck, where he talks from atomic sizes to neutron stars all the way. And it has certain charming features like the universal solution for neutral atoms. which are worth exploring. So this is the charming feature I'm talking about. This is the universal atomic photoabsorption cross section in Thomas-Fermi theory, right? This is the curve, and you can see all the experimental numbers are floating around. So these are the kind of things one can do, one can learn about. So it's worth exploring. So the present work is also an attempt to explore the theory and investigate if it has universal solutions for some other systems. As I said, it can be a challenge to find another universal solution, and when you get them, it's fun. Just to introduce what I mean by universal solution, let me just tell you what the universal solution for atoms is. When you talk about Thomas-Fermi equation for atoms, I start with this equation, right? Note the spherical symmetry and do some jugglery with mathematics. From this, you can write that the density is going to be in terms of the potential like this, right? And the potential is the Hartree minus Z over R, which is the atomic potential. Obviously, since this is an electrostatic potential, it satisfies the Poisson's equation, and therefore you can relate the density to the potential in some other way, and you finally get an equation which is like this, right? By defining all these terms which are related to the electrostatic potential and things like those. I have not yet made it universal because there is this Z sitting around. You want to do that, you start with a B equals this, some coefficient, and then the whole thing reduces to this equation. This is the reduced Thomas-Fermi equation, which you solve and scales by Z. You solve it with the boundary condition that this phi potential has to be 1 because the way it has been defined at 0 and at infinity is 0. Once you solve it, this phi, you can always scale it with respect to the atomic number and get your answer for anything. So the solution for neutral atoms gives you mu equals 0. That is a sort of a bad thing about Thomas-Fermi theory, because mu equals 0 means its ionization potential is 0, which is obviously not true. Solution near 0, and there has been lots and lots of papers talking about numerical solution of Thomas-Fermi theory. It's a non-linear theory, so the solution, finding a solution is really challenging. So near 0, you can do iterative calculation and get this. Since this is a universal equation, the slope comes out to be minus 1.588 and lots of numbers out here. And near x equals infinity, as you go far away, the solution comes out to be again universal 1 over 144 x cubed, which goes as 1 over r raised to 6. So this makes Thomas-Fermi equation universal for neutral atoms, giving energy which scales as z raised to 7 by 3. It also becomes exact in the limit of z going to infinity. So this is the part for atoms. Now we want to explore universality of Thomas-Fermi for neutral Jellium spheres. How we got into neutral Jellium spheres was because I'm looking for a spherical solution, universal solution. I have to start with a system which is spherical, right? And these are systems which have been used quite often to describe alkali metal clusters. So let me just give you a background. The Jellium spheres are n positive charges with density parameter Rs, the Wigner-Seitz radius, spread uniformly over them and electrons moving in it. The background potential is obviously limited to capital R, where R is the radius of the Jellium sphere, and the external potential comes out to be this. So this is like parabolic inside the sphere, and outside it's atom-like. Why do we study them? They are useful because they became a good model to study alkali metal clusters from 1983 onwards, when the group at Berkeley, they produced these metallic clusters and found that they had magic numbers. And then there were 2 reviews of modern physics talking about these. Even recently, I refer to these 2 papers. So these provide a good zeroth order model system for similar systems, right? So it's a good thing to study these, and if you can find some universality, that is even better. Again, like atoms, for neutral spheres, the chemical potential is going to be 0. Like atoms, VR is going to be this. Now we do some mathematics to get universal solutions or semi-universal, as I'll explain later. I take potential to be some form GR by R. I mean, this took some time to realize as to how to write this potential if you want to get a semi-universal solution. And then, electron density can be written in terms of this GR function. With mu equals 0, there is nothing out here, right? And you do that. You do little mathematical jugglery. There's the Poisson's equation involved. This involves two terms. Remember, in atoms, this is minus Z over R only at that. It's a delta function. Here is a spread. So that's what makes it a little more difficult. Then there's the electronic charge. In terms of GR, there's this, all this equations come in. One doesn't have to go into the detail. But you just keep playing with it. And finally, you get this equation, where x is nothing but the reduced radius in terms of the capital R, right? And you get this factor out. Notice inside it's all x, nothing else. And this factor comes out. So this factor can be used to to make this semi-universal. Semi-universal in the sense that once I have this factor, I write this in terms of this factor. For a factor like this, all n and Rs that have this same factor would have the same solution. So here is the semi-universal Thomas-Fermi equation. This is the equation. Boundary condition is going to be at 0, G is going to be 0. At infinity, G is going to be infinity. Going to be 0 again. The factor gives a solution that is valid for all n and all Rs that have this value. So in one shot, I get solutions for many different n and Rs. This facilitates getting solution for a large number of clusters or Jellium spheres by solving a single equation, just like atoms. How do we solve this? Now you can, again, do a lot of mathematics and take the limit of this factor going to infinity. Then you bring it to the left-hand side, this becomes 0, and therefore Gx has the solution here, x equals 0. What this tells you is that as n, this factor goes to infinity, this should be the slope of the solution. The slope at the origin, therefore, is this times some function of this factor. Now, see, once you isolated this factor, everything can be written in terms of that, and that's what you will see. As R goes to infinity, again, it becomes atom-like, because at R equals infinity, this potential is minus 1 over R. So you get, as R goes to infinity, this is the density. So I've gotten two extreme solutions, right? And then it facilitates getting the solution. So you start integrating by this slope and then start decreasing it, right? Slowly to get the solution. Continue integrating up to some xn until the density equals this. I'm going over this because it's a nonlinear equation. Getting a numerical solution is quite tricky. And from that point onward, the solution is taken to be the asymptotic solution, like this. Check if the normalization comes out all right. If everything checks, we found the solution, but we are still not satisfied. We wanted to do something more, which I'll talk about a little later. But what I want to show you here, that for two different f's, I just want to show you the solution. This is our xn somewhere far out here, and these are the solutions. And from this, whatever different clusters I want to talk about, I can generate the solution. For example, if I take f equals 5, I have gotten solution for three different clusters from the same solution. So, and I can generate as many as I like. That's the beauty of the Thomas-Fermi equation and beauty of finding the semi-universal solution. For the complete solution, we transform this equation for Gx using u equals 1 over x. You can see if I'm taking u equals 1 over x, I obviously want to take the limit x going to infinity. Then you can write the equation like this, and the differential equation for this y comes out to be like this. I can now start with u equals 0, that is at x equals infinity, and work inwards to just check my solution. So we take the solution at near infinity as the series. This you can do iteratively, where n comes out to be this crazy number, and then integrate inwards and match the two solutions, and then you confirm the solution is okay. So you start with the value of a naught, integrate inwards from a point u naught, where you take the value of this, and then keep changing a naught until you match the solution coming from inside, right? So again, I'm going over this because this is something one has to keep in mind. How does the discovery of this parameter f n raised to 2 half rs help? I've already shown you this gives you a semi-universal solution. Let me show you how, having found this factor, a lot of things just fall in place. For example, the initial slope as a function of f has this expression. This is quite straightforward except for this exponential part. Again, we played around with it, so finally we found this, and you can see that this slope can be found given an f very easily. We have these numbers tabulated, you plug them in and you have the slope. How good it is? I'll show you. For f greater than or equal to 6, our formula gives you number up to 5 or 6 decimal places. For a nonlinear problem, this is a great help because now I can just vary a few numbers beyond this and get my answer. Otherwise, I don't have to do it right from here. So that's a nice semi-universal feature. For f less than or equal to 6, the parameters are slightly different, but again, you can see I can go up to 4 or 5 decimal places in the slope. Total energy, this comes out beautifully to be a very simple formula. 0.6 over 1.5 plus f n raised to 7/3. Now imagine this. If I were to express the whole energy in terms of n and rs, the f has n raised to 2/3 rs here. Try expanding this and you get all sorts of powers of n and rs. So if you were working in terms of n and the density parameter separately, you would go absolutely crazy trying to find an analytical solution. But having discovered that there is a there's a factor that gives it the solution in a semi-universal manner, we could find this, and this matches beautifully with the atomic formula, which is z raised to 7/3, and this is n raised to 7/3. How good is this formula? Let me show you here. Here is the exact solution of Thomas-Fermi, which we found numerically, and here's our analytical formula. Except for very small f, which we have now corrected, you can see the percent difference is less than 0.5% from f onwards, right? So this one could find the solution precisely because we recognized an important parameter and semi-universality in terms of. We did not stop here. We also tried to find how does the energy, Thomas-Fermi part of the energy compare. Suppose you took a variational Monte Carlo, very exact calculation of these clusters which exist in literature, and we compare the Thomas-Fermi part of the energy with VMC, the variational Monte Carlo, and you can see we're very close. So finding discovery of that factor and that formula really is very, very satisfying. And I was just listening to Professor Sen's talk, and he was talking about confined hydrogen atoms. We can actually with this do confine many things, and with large number of electrons. And maybe we can find a formula like this. This is a very different potential from atomic potential. We can go to any other potential and see if there are any universality that we can get. So finally, with that, I summarize. We have applied Thomas-Fermi theory to Jellium spheres. We have developed a semi-universal solution for these systems. The solution facilitates calculating properties of a large number of such systems. Work is underway to take further advantage of semi-universal nature of these solutions. With that, I thank you very much for your attention.
Swayam Prabha, Digital India, Educated India.